thought I had the screen set up. I haven't moved the whiteboard over to the left and up as far as I can. So let me get that done. Okay. All right. We are now sharing. You can see the whiteboard, right? Okay. All right. If there are no questions, I guess we'll go on and get started. We're in Chapter 3, Determinants, in Section 3.3, Properties of Determinants. And we just talked about theorems 3.5 and 3.6. First, what is the determinant of a matrix product? Well, it's the product of the determinants of the two matrices, which is, I don't know, I found a little surprising, but it works. Okay, and then secondly, the determinant of a scalar multiple of the matrix, that would then be that scalar multiple raised to the nth power. If this, remember, to be a determinant, it has to be a square matrix, an n by n matrix, so it's c to the n times the determinant of the original matrix. And we did example 2. I'm sorry, I can't remember if I had this yesterday or not, but my throat is pretty sore. I think it was a combination of smoke, because we were burning a lot at the farm over the weekend, and so a combination of that and the fact that we've had a weather change and it's gotten quite a bit cooler, and I'm got a sore throat from one of those two or both. I don't know which. And I was also doing a lot of mowing out in the yard, and so there was lots of pollens and other things that were being stirred around too. I had a mask on, but obviously it wasn't completely effective. Okay, so anyway, these two theorems we've just talked about give formulas for the determinants of a product of two matrices and a scalar multiple of a matrix. However, they do not give a formula for the determinant of the sum of two matrices. Okay, now the sum of the determinants of two matrices usually does not equal the determinant of their sums. Okay, so in general, you can summarize what we just said then. If you have a matrix A and take the determinant of that and add it to matrix B, the determinant of matrix B, in general, this is not going to be, and there's no reason to expect it to be, the determinant of A plus B. It just doesn't happen. Okay, so don't expect that to happen. Okay, and they give you two really simple ones. Matrix A is 6, 2, 2, 1. Matrix B, let's do the determinant of B, would be 3, 7, 0, negative 1. Okay, what's the determinant of A? 6 minus 4 would be 2. The determinant of B would be negative 3. Okay, well, what happens if we add these two together? A plus B. That's a pretty simple operation. That would be 9, 9, 2, and 0. Okay, if you add those together, now take the determinant of that, and what do we get? That would be negative 18. No connection here at all. Okay, none whatsoever. 2 plus a negative 3 would be a minus 1, nowhere close to negative 18. Okay, so nope, no correlation there. The product to two matrices is the product of their determinants. Okay, the determinant of the product of two matrices is the product of their determinants, but nothing doesn't work for sums or differences. Okay, so how about another property that may or may not work? Okay, let's do look at the determinants of and the inverse of a matrix. Okay, let's take a look at these two. I think I'll go on and clear my screen here. Okay, here is matrix A. Now, because I'm going to turn around and do a determinant, I'm going to leave, well, no, I'll just go and write it in. Okay, 0, 2, minus 1. 3, negative 2, 1. 3, 2, negative 1. Okay, I hope I copied them right. Looks okay. Here's matrix B. 0, 2, negative 1. That looks familiar. 3, negative 2, 1. And 3, 2, 1. All right, two matrices. Now, the question is, can you look at those two matrices and tell whether one or the other has an inverse or not? Okay. Now, if you remember that some of the qualifiers of whether something has an inverse or not is if two rows were multiples of each other, then you know that matrix does not have an inverse. Neither one of these, that's the case. I mean, there's some similarity, but it's just not the case. Okay. But if you remember, when we're dealing with determinants, it's not just the rows that you worry about. You can also consider the columns. And in this one, the column 2 is an exact multiple of column 3. So therefore, the determinant of matrix A is going to be 0. And if the determinant of a matrix is 0, that matrix does not have an inverse. Okay, I don't know if we hit that yet, but we're going to. Whereas this one, rows or columns, neither of those are multiples of each other. Now that still doesn't guarantee that it does have an inverse, but at least this one, you know, it doesn't have an inverse because this column is a multiple of that column. This one, there's no such column or row here, but the indication would be it would be more likely to have an inverse than the other. So that leads to theorem 3.7. And I think I will type this one in just because probably it's going to be easier to read and perhaps even easier to write. So let's type in theorem 3.7. Okay. Goodness, my hands are so cold now that it's gotten chilly. Since I've only been teaching from home since last basically March, and March wasn't bad. Okay, it was nice weather by then. This is the first sort of cold snap we've had, and because of the cold snap, this is the first time that I've been teaching from home, and usually we have our thermostats cut back in the daytime because we're not here. Well, this is the first cold weather we've had. I've had to turn up both thermostats, upstairs and downstairs, just so I can manage when I'm still pretty chilly. And with a sore throat, and that, it just magnifies it. So here's theorem 3.7, determinants of an invertible matrix. Okay, a square matrix A is invertible. Now, that another word for invertible is non-singular. If and only if its determinant, I'm going to draw it this way, determinant of A is not equal to 0. Uh-oh, I forgot that. I was thinking this doesn't have any symbols in it, but it does have a symbol. And there is no not equal to symbol on my computer screen. On my keyboard, I mean. So I'm going to have to just type it in. Okay. Now, okay. So sorry about this. I didn't realize that was going to be the case. I'm going to now see if I can draw here. That's not equal to 0. A square matrix A is invertible or non-singular if and only if its determinant is not 0. It can have any determinant in the world except 0. If it has a 0 determinant, that matrix is not invertible. And if that determinant is anything other than 0, it is an invertible or non-singular matrix. Okay. Now they do a proof under that. I'll let you go through the proof. It's pretty straightforward, I think. Let's look at the discovery that's on page 128. Okay. And unfortunately, it says use a software program or a graphing utility to find the inverse of this matrix. I think I've done this before and I've not been happy with it, but I'm going to see if I can do it. So I'm going to clear the drawing here and let's see what we get. Okay, here's I'm sorry. Here's the matrix A. Okay, 6, 4, 1. Okay, I'm going to find an inverse, so I'm going to follow that with the 1, 0, 0. We're augmenting the identity matrix to it. 0, 2, 3. 0, 1, 0. And 1, 1, 2. 0, 0, 1. I'm probably going to regret doing this, but let me approach it. And if it gets too hairy, I'll just quit, okay, and say get you a graphing calculator or some type of package and do it on your own. That's what they suggested. Okay, now first thing we want is a 1 to be in the upper left. We have a 6 there. So I'm going to exchange these two rows. So I'm probably not going to write in all the steps here, but let's do it this way. So the first row is now going to become 1, 1, 2, 0, 0. Yuck! I hate this thing. Okay. 0, 2, 3, 0, 1, 0, and 6, 4, 1, 1, 0, 0. Okay, what we want to happen next is that 6 to become a 0. So we'll do minus 6, row 1, plus row 3. Okay. I wish I had room for it. I don't think I will, so let me go down here, and that will be 1, 1, 2, 0, 0, 1. 0, 2, 3, 0, 1, 0. And negative 6 times 1 is negative 6 plus 6 is 0. Negative 6 times 1 is negative 6 plus 4. Negative 6 plus 4 is negative 2, I hope. Okay, I'm sorry. I'm going to have to get another swig of something. My throat is getting too raw. I don't know whether the sugar helps or not, but it's pretty sore. All right, going back to where we were. Negative 6 times 2 is negative 12. I think that's a 2. No, that's a 1. Negative 12 plus 1 is negative 11, I think. The brain is not working well today. Negative 6 times 0 is 0 plus 1 is 1. And negative 6 times 0 is 0 plus 0 is 0. And negative 6 times 1 is negative 6. All right. Now, next thing we want to happen, I'm just going to add the bottom two rows together. This probably isn't the preferred mechanism, but I'm just going to do it. Okay, we're going to add row 2 and row 3. So that's a 1, 1, 2, 0, 0, 1. A 0, I'm leaving row 2 alone. 0, 2, 3, 0, 1, 0. And adding the second and third row gives you 0, 0, negative 8, 1, 1, negative 6. Okay. Now, things are not looking good, and I don't think they're going to get much better. Okay, but let's see if we can do this. Let's next divide row 2 by 2. Okay, this is why they said use a device to do it. 1, 1, 2, 0, 0, 1. 0, 1, 3 halves, 0, 1 half, 0. And zero, 0. I'm real tempted to go on and divide that one by negative 8. So that would give you a 1, negative 1/8, negative 1/8, and 3/4. My writing sort of stinks there, but we'll go with it. Okay, I'm getting chilled again. Sorry about that. Okay. Next thing we're going to do is negative row 2 plus row 1. Okay, to try to get that to become a 0. That should work, I think. Alright. Middle row we're leaving alone. 0, 1, 3 halves, 0, 1 half, and 0. Okay. And then minus row 2 plus row 1. 1, 0, negative 1 half, I think. Okay. 0. Okay, I can't get my pen to show up. There it is. 0. Negative 1 half. And 1. Okay. And then we have a 0, 0, 1, negative 1/8. I'm sorry, negative 1/8 and 3/4. Okay. Now we're almost there. Not pretty, but almost there. Okay. So what we're going to do next is minus 1 half, no, 1 half times row 3 plus row 1. Okay. So we have a 0, 0, 1, negative 1/8, negative 1/8, 3/4. All right. And 1 half times row 3 plus row 1. 1, 0, 0. Okay. Okay, I'm sorry, I'm losing my voice completely, sorry. Okay. 1 half times row, sorry, row 3 added to row 1. That's what I'm trying to get my pen to show up. So 1 half times a negative 1/8 is a minus 1/16. And then a 1 half times negative 1/8 is negative 1/16 minus 4/16. So that's negative 5/16, I think. And a 1 half times 3/4 is 3/8 plus 4/8. I mean 8/8 would be 5/8. Okay, wait. No. 3/8 plus 8/8 is 11/8. Okay, sorry. I'm getting to feel pretty miserable here. I don't know. Okay. I'm not thinking clearly either, so this is getting bad. That would be 3/8 plus 8/8 would be 11/8. All right. The next step here is minus 3 halves times row 3 added to row 2. So that'll be a 0, that'll be a 1, and that will be a 0. Okay. Minus 3 halves times a minus 1/8. that's going to be a 1/16 plus 0 is going to be a 1/16. Same thing here. A -3/2 times a -1/8 is going to be a minus. I think I just did that one wrong. Like I say, my thought process is not great here. Okay. -3/2 times 1/8 would be a minus 3/16 plus, no, positive 3/16. So I think this is a 3/16 here. And a -3/8 times -3/2 times a -1/8 would be, again, a positive 3/16 and a positive 4/16, no, 8/16. I think that's 11/16. Okay, and then finally a -3/2 times a 3/4 would be a -9/8, I believe, -9/8. Now again, I'm not guaranteeing any of this. I'm feeling so rotten right now. That, I think, is your inverse matrix. Now it says, now compare the determinant of that inverse matrix with the determinant of A. Okay, so let's first do the determinant of A and see how messy this gets. And here's somebody else coming in. I believe it's James. Okay, so let me let James in. So doubled the class size in one fell swoop. So the top two are here, the bottom one is not. Hopefully Jesus will be coming in shortly. James, we're probably ill-advisedly doing the discovery on page 128. Sorry. Chapter 3, Determinants, section 3.3, Properties of Determinants, and we're doing the discovery on page 128 in the left-hand margin. There was our original matrix, 641,023,112, and we just have, not using a software program or a graphing utility, but found, I hope, what is the determinant, which is down here. It's really messy, but hopefully it's right. Okay, I can't guarantee it's right. Now, it says compare the determinant of the inverse with the determinant of A. So just because it looks like A may be a little easier, I'm going to do that one first. Okay, and I don't have a lot of room, so I'm going to try to squeeze it in somewhere down here. Okay, the determinant of A. And since that's a 3 by 3, I'm going to do 6, 4, 1, 6, 4. 0, 2, 3, 0, 2. And 1, 1, 2, 1, 1. Okay, now this is doing a determinant, so to speak. Let's do our down diagonal here, and that would be 4 times 6 is 24. Next down diagonal here is plus 12, and the last one is a 0. Okay, now erasing those two lines there. I hope I didn't erase things I wasn't supposed to. I did, but I don't think it would matter. This was a 0 here, but that's not going to impact anything here. Okay, let's do the up diagonal is a -2. Up the next diagonal is a -18. And up the final diagonal is a 0. Okay, so this is a -20, plus 24 would be a +4, and 12 would be 16, I think. Okay, now that's the determinant of A. Now to do the determinant of the inverse, and there's no guarantee this is going to be right, but I'm going to try it. Okay, I'm going to factor out a -1/16. Okay, and do a determinant of what's left. 1, 5, I think it's a 22. I may be wrong on that, but I believe it's a 22. Only it's a minus. Okay. And that will be a -3, -11, and a +2. And then the next one's going to be a 2, a 2, and a my brain's not working well. I think that's going to be a 12. Okay, I can't tell for sure, but I believe it's going to be a 12. Like I said, my brain's not working well, and my pen doesn't seem to be working at all. Let me see if that's right. Okay. -1/16, -5/16, +11/8. I believe that's right. A +3/16, a +11/16, and a -1/8, and a -1/8, -1/8. The sign's wrong. Okay, I think that's right now. That would be a +12/16, which I think is 3/4. Yeah. Okay, now if I did the inverse right, I think that's it. Okay, now remembering our last theorem that if A is a square matrix of order n, C is a scalar, then the determinant of CA is C to the n times the determinant of A. Okay, so it's a 3 by 3, so it's going to be a -1/16 to the third power, okay, which would be a negative (1/16 times 16 times 16. I can't do that one in my head. Goodness, I'm feeling rotten. So 16 times 16 times 16. Wow. 4,096. Okay. $4,096. Okay. Wow, that's going to be a big number. Okay. But we still got to do the determinant of that, and that's going to be a big number too. So I'm going to do this up here, and okay, that's a 1, 5, negative 22, 1, 5. Negative 3, negative 11, 2. Negative 3, negative 11. Yuck. Okay. 2, 2, negative 12. 2, 2. Okay. Now, I'm going to try to do this just with the calculator, okay, because I don't want to write down all these numbers. That's I think a negative 11 times a negative 12, which is going to be 11 times 12, plus 20. Okay, plus 22 times 6, I think it is. Equal. Okay. Then I'm going to do my up diagonals, minus 22 times 22. Okay. Minus 4. Minus 36 times 5. A minus 384. Okay. Now, that's my numerator, I think. I'm going to divide that by 4096. Okay, and I get a 0.09375. Okay, now I'm going to turn my sideways things crooked and do a reciprocal of that, and I get the wrong answer. Okay, I think it's supposed to be exactly the reciprocal, and I got a negative 10.6, and I've just made an error in my calculations. Sorry about that. Shouldn't have wasted that much time doing it. But here's the conjecture about the determinant of an inverse of a matrix. It's 1 over the determinant of the matrix. Okay, I'm pretty sure that's going to be the case, and we're going to see that in just a minute, and that's indeed what we got. So let's do, sorry that I wasted so much time on that one. Let's clear the drawing out of the way, and let's do, now did someone else try to come in? I've got this thing blocking the view. Nope, it's just got the two of you. Glad y'all are here. I don't know where Jesus is, but hopefully he'll be coming in. but we are running out of time. We go to what, 12:45? Yeah, so we've got some time to go. Okay, so example 3 says determine whether each matrix has an inverse. Okay, and if I can get my pen to write, there it is. Okay, I think these are the ones we did at the top, weren't they? Yes. And so we've already done this. We didn't take the determinant, but we could. In fact, let's do that determinant. That one at the top was 0, 2, -1. And we'll just repeat the first two rows, 0, 2, the first two columns. 3, -2, 1. 3, -2. 3, 2, -1. 3, 2. Okay, now that one we had already determined is not going to have, that's going to have a 0 determinant. Let's do our lines down here. That would be a 0. This will be a 6. And this will be a -6. Okay, now I'm going to try to erase those 3 lines. That's so aggravating. Okay, I'm going to try it one more time. Okay, and let's do the up diagonals. Goodness gracious. That's going to be a -6. This is going to be a 0, and that's going to be a +6. And sure enough, they add to 0. 0 plus 0 is 0. All right. Now we'll do the other one. A 0, 2, -1. 0, 2. A 3, -2, 1. 3, -2. And as 3, 2, 1. 3, 2. Okay, let's do that. Okay, again, that one's going to be a 0. That one's going to be a 6. And this is going to be a -6. Doesn't look good. That's still 0. Okay, but let's erase. Well, up there it goes. Erase that one, that one, that one, and draw back in the up diagonals. It's going to be a -6. It's going to be a 0, and that's going to be a -6, which is -12. So that one does have an inverse. That's not 0. All right, so here is the theorem that the discovery was leading toward, but I didn't get it done. Okay, I'm going to write this one in, I think. If A is an n by n matrix, okay, square matrix, and not only is it square, it is invertible. Okay, so square invertible matrix, then if that's given, then the determinant of A inverse, because the A inverse does exist because it's an invertible matrix, is 1 over the determinant of A. And that's exactly what I suspected, but I must have made just one dumb mistake on the other one, and it didn't come out true. Okay. Now, let's move on to example 4. Oh, my throat is hurting. Yeah. It says find, I think I'll clear the screen here. Anyone need that a little bit longer? Okay. Oh, man. Find the determinant of the inverse for this matrix. Here's the matrix. A is equal to, and we're going to be doing to the, I'm going to give it away. We're going to do the determinant first. Okay. The matrix is 1, 0, 3. Now I'm going to repeat the 1, 0. 0, negative 1, 2. 0, negative 1. And 2, 1, 0. 2, 1. Okay. Now what they wanted is the determinant of the inverse of that matrix. But being the lazy person that I am, with a really sore throat, I'm going to do the determinant of this first. That's going to give us a 0. That's going to give us a 0. That's going to give us a 0. So we get nothing with our down diagonals. Okay? So that gives us absolutely nothing. Okay? Now, let's do the up diagonals. That's going to be a positive 6. This is going to be a minus 2. And that one's going to be 0. So this is going to be 4. That's the determinant of A. So the determinant of A inverse from our last theorem is going to be 1/4. Now, that was a lot easier than finding the inverse of A and then finding the determinant of that inverse. Okay, so I did it the very easy way. Is first determine the determinant of A, because that's a fairly straightforward, lots of zeros in it, not going to contribute a lot, and then it's an easy determinant, and then do the since we don't really want to know, we don't need to know the inverse of A, we just need to know its determinant, then just do 1 over that. Now, that leads to another set of equivalent conditions. I'm trying to figure out now whether I want to write these in or type them in. And since they do have some subscripts, I think I will write them in. This is not going to be pretty. Okay. What we have here is that A is an n by n matrix. Okay. A is an n by n matrix. Then the following conditions are all equivalent. Okay. Number 1. A is invertible. Okay. Now, we didn't say that originally, just said it was square. Okay. In order to be invertible, it's got to be square. Okay. But just because it's square doesn't mean it's invertible. But now we're telling you it is invertible. Okay. Now, with that in mind, if A is invertible, that means that AX, where X is a column vector, your unknown column vector, is equal to B, which is another column vector, but this is a known column vector, B, that has a unique solution for every column matrix B. For every column matrix B. Okay. Now the third one is awfully close to that too. That AX, if that's equal to the 0 vector, okay. Now they write the number 0, which I don't agree with, okay. That is a vector 0, but they just about every time does it. That has only the trivial solution. Okay. Well, of course it would. If the number 2 is true, that B is the 0 vector, and that's a unique solution, and you know that then the 0 x's would have to give you that same thing. That's the only trivial solution. So those two follow hand in hand. Number 4. A is row equivalent to IN. Yeah, because that's how we find the, if A is invertible, you just do the row equivalence and you'll come up with the identity matrix of that size. Okay. Now the last thing that we did, we said that A can be written as the product of equivalent matrices, of elementary matrices. A can be written as the product of elementary matrices. Okay, and number 6. The determinant of A is not equal to 0. Okay, that means that's invertible. All of those indicate invertibility, and all of those, any one of them, invertibility implies every other one. Okay, so all those are equivalent. Okay, now let's see. Let's do example 5. All right, to erase. Okay. And it says here, which of the systems has a unique solution? And I hate doing this, but I'm going to do it. Okay. Here is 2x1 minus 2x2. This is so rotten. Two x2, if I could write, minus x3 is equal to minus 1. 3x1 minus 2x2 plus x3 is equal to 4. 3x1, that is a positive 3, I don't know why it has a tag on the end, plus 2x2, maybe this isn't the same one I was thinking of, minus x3 is equal to minus 4. Okay. Oh man, I am getting almost cramped. Okay, here is the second system of linear equations. Okay, everything is the same as the first one except for this, plus x3 in that last entry here. This is the only thing that's different. Everything else is identical. Okay, now it says which of these has a unique solution. Now, what I originally thought, and I still think I'm right, I'm sorry, I'm feeling pretty rotten. If we did our coefficient matrix, okay, here's what it would be: 0, 2, minus 1, 3, minus 2, 1, 3, 2, minus 1. Over here it would have been a 0, 2, minus 1, 3, minus 2, 1, and 3, 2, minus 1. Okay. No, 3, 2, 1. Okay. Now, here's why I didn't want to have to write everything down. And basically I didn't. If you look at those two matrices there, you'll see they're exactly the ones at the top of page 128, which we've already done. They're exactly the ones in example 3 of 128, which we've also done. So why do them all again? But we see that this, the determinant of this one, is equal to 0. Why? Because these two columns are multiples of each other. This one we did before, and I think came out to be, the determinant I think was a minus 12. I can't remember for sure. Yes, it was. So this one does have a unique solution when everything else is the same except that minus 3 becomes a plus, minus x3 becomes a plus x3. All your other things, everything else is identical, then that will have a unique solution. Why does it have a unique solution? Because the determinant is not 0. The determinant of the coefficient matrix is not 0. Okay. The final, goodness, my throat hurts. The final topic or subject or whatever you want to say in this section is determinants of a transpose of a matrix. So let's clear the drawing here. And I don't know, I'm just feeling antsy. I don't know what's the problem. I'm a little too chilly, and that's part of it. And I think this has to do with my anemia too, because I have noticed over the weekend when we were outside, my hands would get cold and I could not get them to warm up. and that's never been the case with me. I'm always just in no time I can warm up, and now I cannot. So I'm feeling pretty rotten right now. Okay, the next theorem tells you that the determinant of a transpose of a square matrix is equal to the determinant of the original matrix. Okay, it says the theorem can be proven by mathematical induction and theorem 3.1, which we've just recently done, which state that the determinant can be evaluated using cofactor expansion in either a row or a column. And it says the details of the proof left up to you, which knock yourself out. So here is that theorem. If, I don't know, this is just feeling really rotten. If A is a square matrix, okay, then the determinant of A is equal to the determinant of A transpose. Okay, that's it. That is the theorem. If A is a square matrix, now that doesn't mean it's an invertible matrix, okay? Just means it's a square matrix. If it's invertible, then its determinant is non-zero, but if it's not invertible or singular, then its determinant is zero, okay? But then its transpose, which it can have a transpose even if it's not invertible, the transpose will also have a zero determinant, meaning it's not invertible either. Okay? Now, example 6, you can go to larsonlinearalgebra.com for an interactive version of this type of example. Okay, so here's a matrix A. Three, 1, negative 2. Two, 0, 0. Negative 4, negative 1, 5. Okay. Now, what we want us to show is that A, the determinant of A is the same as the determinant of A transpose. Okay. Now, let's first do the determinant of A. Now, normally I would expand, but since this has two zeros right there, let's just use our cofactor expansion. Okay. Now, that 2 right there has the position of a negative. So that's going to be negative 2 times the determinant of what's left over. Okay. That would be 5 plus 2 is 7. So that's going to be negative 14. Okay. Now, let's do the other, A transpose. A transpose would be 3, 1, negative 2. That first row here becomes the first column there. 2, 0, 0, and negative 4, negative 1. This pen is not drawing well. Let me see if I can clean that up some. Four, negative 1, 5. Okay, now if we're doing the determinant, guess what? You do the same thing we did before. Pick this row and that column, and that again is in a negative position, so it's going to be -2 times the determinant that's left over, 5 minus 2. Well, it would help if I could multiply. Yeah, that's 5 minus 2, not plus 2. That would be 3, so that would be a -6. And this would also be 5 minus 2 is 3. So that would be -6. They're going to have the same determinant. Okay, both of them -6, if I could just have done them properly. Okay, there is a linear algebra applied right at the bottom of page 130, and that is dealing with systems of linear differential equations often arise in engineering and control theory, and for a function f of t that is defined for all positive values of t, the Laplace transform f of t is capital F of s, which is equal to the integral from 0 to infinity of e to the minus st e to the minus st times f of t dt, provided that the improper integral exists and Laplace transforms and Cramer's rule uses determinants to do that. So here you have several things here. Who in the world is Laplace? How did he come up with these transforms? Who uses these transforms? Hint, hint, electrical engineering uses Laplace transforms big time. Other people do too, but they do. Here's Cramer. Who was Cramer's rule? Who was Cramer? How did he develop this rule? Who uses it? Lots of possibilities there for paper topics. Hint, hint. Please don't forget your research papers. Homework exercises here in 3.3. Any of the odds 1 through 5, they're all at Calc Chat. 7 through 13, they're all at Calc Chat. 15 or 17, both at Calc Chat. 19 through 23, all at Calc Chat. 25 through 29, all at Calc Chat. 31 through 36, all at Calc Chat. 37 to 41, all at Calc Chat. 43 to 49, all at Calc Chat. 51 to 55, all at Calc Chat. 57, any of the odds 57 through 69 should all be at Calc Chat. 71 should be at Calc Chat. 73 through 77 should be at Calc Chat. 79 should be at Calc Chat. 81 should be at Calc Chat. And 83 should be at Calc Chat. Now, they do something that irritates me, and I think I've already mentioned it before. They give you some new definitions in the homework exercises, not in the text. Okay, and why they do this, I don't know. If it's important enough to be here, why don't they give it to you in the text? But this is something on the definition of an orthogonal matrix. So there it is, defined, and some exercise. I'm so sorry, my throat hurts so badly. But right at the end, they were giving you some definitions and meanings of orthogonal matrices and some applications or properties of them. All right, let's move on to 3.4. This is the last section in chapter 3, so I would say possibly Thursday, I'll be giving you your chapter 3 test. If not, it'll be early next week. Okay. These in 3.4 are applications of determinants. The first of these is finding the adjoint of a matrix. Well, first, what in the world is an adjoint, and how do we use determinants to find those? Okay. Next is Cramer's rule, which we were just talking about. Using Cramer's rule to solve a system of n linear equations in n variables, as if we haven't done enough of that in other ways. And then finally, using determinants to find area, volume, and equations of lines and planes. And I am just freezing. I don't know why I've got the heat up and everything, but this is not feeling good. So far in this chapter, you have studied procedures for evaluating and properties of determinants. In this section, we'll study an explicit formula for the inverse of a non-singular matrix and use that formula to prove a theorem known as Cramer's rule. You also use Cramer's rule to solve systems of linear equations and study several other forms or applications of determinant. I'm sorry, my throat is hurting so badly. I do think I have a mint here. I might try that in a minute. Okay. Now, if you recall way back from section 3.1, we talked about cofactors. Okay? And we talked about the cofactor of a square matrix A is the plus or minus 1 times the determinant of a matrix obtained from deleting the ith row and jth column of the matrix of cofactors. Okay? A lot more blah blah blah. Okay? That matrix of cofactors has the following form. Now this is tedious at best, and we only have 1 minute, so I think let's just hold off on this because there's no way we're going to get this done in a minute. Okay? And we didn't get enough done here to cover that, so we will start right there talking about the matrix of cofactors. Okay? And that's going to lend itself to what an adjoint of a matrix is, and then from that we'll be able to solve a system of equations. Okay, so those are beginning of what we're doing with applications of determinants. Now, because these are going to be somewhat lengthy to do, I doubt if we're going to finish. Yeah, this is a long section. We won't finish this, so it'll probably be next week before we get to the chapter 3 test, which means gives you a little more time to get the chapters 1 and 2 tests done if you haven't done them. I can't remember if both of you have done those or not, but I know I don't have them all in, so I just can't remember who is missing what. But anyway, we'll deal with that later. Any questions on what we've done so far in chapter 3? All right, we'll wrap it up then, chapter 3 next week, and move into chapter 4. Okay? Well, we've still got Thursday of this week. We may actually finish 3.4, but I kind of doubt it. All right, any questions? I'm going to stop sharing here if I can just get this to stop sharing. Okay? And we missed Jesus today. Hopefully he'll be back tomorrow because all of us are together again tomorrow. So take care, people. Stay warm. Take care of yourself. We'll see you tomorrow and Thursday. Good deal. Thanks. No questions? Okay, we're going to end the meeting for everybody.